Kappa analysis is a good way to check the quality of your pass-fail quality control checks. So you're basically checking those operators or machines that make your pass-fail decision in the factory. Hello, I'm Tom. Welcome to my channel where we discuss continuous improvement in an industrial setting. And this video specifically is on Kappa analysis, or Cohan's Kappa. It is part of the measurement systems analysis. So we are talking about a measurement system, and specifically here it's the sort of binary measurement of a pass-fail criteria. You know that we've been talking about R&R analysis, gauge R&R. This is about measurement systems that use a continuous scale. Now we are talking about when we check this product is good or it is not good. And also for this type of measurement, you want to know if I've got two operators, two quality control people, right? So, and I give them the same product, will they also both say it's good or both say it's bad? So how stable is the measurement system itself? This is not really about the product, right? It's not about the defect percentage I have in my production. It is about, do my testing operators, my QC people, do they agree on the same products being good, the same products being bad? Now, pass-fail is the most commonly used thing here. Maybe you have sort of A, B category. You can use it for any system where you have two options, right? Every product is put either in the one bin or the other, but then pass-fail, of course, is the most common way to do this. We will go over how you do this Kappa analysis. And as you see, I already wrote it out, there will be quite a bit of formulas in here. I will try to keep it as simple as possible, but also explaining what it is doing and why these formulas are in that order and why the different things are in there. And then we'll also go into how to use it in practice, because we will see quite quickly already that you can only use it for two operators, and that might not serve all your purposes. So stay tuned for that. How do we use it in a more practical setting? So Kappa analysis. What it is, and we'll use the pass-fail here, a check between two test operators, two quality control people. We have operator A, who considers a product to be good or bad. And now we of course want to know operator B, do they think the product is good or bad? In the ideal world, all of the products that operator A would set aside as good or scrap as bad, if we give those same products a bit mixed to operator B, they will pick out exactly the same products to keep in a good pile or to scrap as bad. Because that way, then we have a very good measurement system, right? So when both of the operators do exactly the same thing, we have a good trust that at least the precision of our measurement system is good. It may still be that they are both wrong, but just like gauge R&R is not a calibration, it cannot tell you if all of your operators, all of your measurement systems are all correct or wrong. It can only tell the difference between them. Kappa analysis has a bit the same thing. So you do calibration to see if you hit the target. You do this Kappa analysis to see if your different testing operators, QC people, whatever, give you the same result. Now, that means that when we put it into sort of a truth table, but we put it into this 2x2 grid, we can have the option that operator A calls it good or bad, times B calling it good or bad. So we have good, 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 bad, bad, good, and bad, bad. What we, of course, would like to have is agreement. So this is one of the things we will also need for our calculations. The rate of agreement is how many GGs and BBs, so good, good, plus how many bad, bad we have, and we divide that by all of them. So the way that you use this table is you will take, for instance, 20 different products. You will hand them to operator A and to operator B, the same 20 products preferably, because otherwise it's very difficult to compare. You know which products are which, what the other person said, operator B should not know what A said, right? They do not converse and make an answer together, separate assessments. And then when your first product is good, you just put a tick there, you get your first one, and like this you count all of them. So in the end what you get here is something like 12 were good, and 5 were bad, and then 2 were judged good by A and bad by B, and 1 was the other way around, bad here, good there, and you get numbers here. So you do not write these codes, you get how many products that were tested in these combinations by both of your QA people. Then you divide that by 20 in our example, so the total number, you add them all up. And we compare that to what we would statistically expect to happen. Now, we don't really expect that there is a certain percentage of good or bad, because we don't really know. We'll just take that from this same set of data. And now if we assume that, for instance, we have a 20% defect rate, we then sort of assume that the operators will cling to this defect rate. So they will have 16 good ones and 4 bad ones, but they pick them almost at random. If they do that, and that is how this Kappa coefficient is built up, if they would do that, we can calculate, based on the observed defect rate, what the different squares here would have been. And the formula for that, and this is the tricky formula, it says, basically, we are going to check what operator A called good. You see these good here. And we are going to times what operator B calls good. So there's again the good, but this time the bad, good. So this one. This added together times that added together. So that is saying the good rate of operator B times the good rate, the good rate of operator A times the good rate of operator B, plus the bad rate times the bad rate. So times this one. So that's basically how, sort of the logic behind it. I haven't explained why it does it, but I think you sort of feel that like this, it can give you a predictor of how much do I expect in which of the squares. This then is divided by the square root of the total number. And that is because we have counted all of them double, been multiplying it, so we've basically been not also squaring the number of results. And that one, in this case, would be the 400, right? 20 times 20 for my example, if there are 20 here. This will give us sort of it's a percentage, sort of, right? They will generate numbers like 0.5 or 0.8, but these are basically 50% agreement or 80% agreement. Now, what you will then see is that to calculate this Kappa result, we take the agreement minus the expected value and we divide it by 1 or 100%, but 1 minus the expected value. And that means that if the expected value is lower than the observed agreement, so this one's big, that one's low, we will get a positive number. But if the observed agreement is lower than what we expected, we'll get a negative number. It is basically even worse than random chance. If they are the same, that is sort of the definition of they just picked it randomly. Now, those you will not often see, right? So you will almost always see, because we didn't put into place completely nonsense quality checks, you'll almost always see a positive number here. And the bigger the expected agreement, the sort of more difficult it becomes to really get good values from this. Now, I will not bother you with all the statistics behind it, but the practical implication of this, the practical effect of this, is that when you set up a Kappa studies, you are trying to aim for a defect rate of, something like 15+%, or at least to have 5 minimum defects in the pool that you are checking. So you can pick, and in theory it would be the best, to pick just random products out of your production. But if you have a defect rate of less than 1%, you would need to pick loads and loads of products. You need 500 at least products to put in your comparison test, which is way too many to ask of operators to do. So what we will generally do is not pick them at random, but we make sure that there are a couple of defects in there. Right, so you get a couple of defects, you do sort of try to randomize it, because if you pick very obvious defects, it'll be too easy for the operators to get that difference, but you try to up that defect rate a bit and make sure that you have got 5 to 10 defective products within the whole mix. If you can get, and there are even people who would advise you to pick a sort of a 50-50 number, that is because these mathematics will be the strongest at 50-50. I would get somewhere in between. So most of our processes don't have a defect rate of more than 5%. So if you pick a 50, it'll feel so unnatural. Go somewhere for about 20-25% of the products being defects, right? Somewhere around that. Otherwise, people will just really start doubting themselves. But when you have that, you give it to those 2 people and you fill out the table. Then you do the calculation. You do the calculations based on their own results, by the way. So if you pick out 25% of bad products, those are not the numbers you stick in here. You still use what they pick out. We then get a Kappa value, and if it is over 0.5, it's sort of acceptable. We are looking for Kappa values that are over 0.7, 0.75. It would be nice if it is 0.8, 0.9. You don't see it that often. So we are looking for definitely higher than 0.5, preferably higher than 0.75. But now, the big sort of problem with the Kappa analysis. We had the one with the defect rate, that you need at least a couple of defects, at least 5, so get your defect rate artificially high in the sample that you take. The other really big thing is that the Kappa analysis will only compare 2 operators. This is a 2-way system. Now, there is a different way of calculating it, and it's not a different Kappa, it is a different way of setting up a comparison of pass-fail tests that can handle multiple people and compare all of them together. That is even more involved. There is another way that in practice gives just as good results for you if you're just interested in checking the measurement system. And that is to have a gold standard that you compare each time 1 by 1 your operators, your test operators do. So instead of having A and B compared and then have a C and a D and an E, so if we have 5 people doing these tests, you would like to do this a couple of times and it doesn't really work. We will make a gold standard. So we determine which of the products are good or bad. And then we check A to the standard, B to the standard, C to the standard, D, and E to the standard. And each of them will get their own Kappa score with the same rating. If it's under 0.5, we need to discuss. If all of them are in the 0.5 or so range, we've got a serious issue with our measurement system and probably with our standards of what is pass and what is fail. If we have 1 or 2 people that are way below the rest, we know we're more looking into training those 2 people. Right? But how do we get this golden standard, right? we are going to do it in a committee. And that committee is the sort of the best quality-minded people of your factory, of your organization. Now, when you do this, you immediately check the quality of your standards, and this is what makes it such a great tool to use in practice. Right, so if we really dive into the statistics behind it, maybe the other comparison technique is slightly better, but this has a very nice added advantage. When we get our chief quality person with the chief technology person and the chief product person, we get them together, and they don't need to be the main manager of the departments. They need to be sort of the people that decide what is good or bad in our product. Those are often the people who complain the most about our operators cannot do these quality checks in a good way. So you got exactly the right people now. You let them discuss, you give them your 20 or so, maybe a bit more, maybe at least 5 to 10 bad products. If you go for a 25% defect rate, it would be nice to have about 40 products. Depends on how difficult it is to test it. But you give them openly those products that you're going to be testing with persons A to E. And you're going to ask them, for each of those products, is this one good or bad? And they can discuss it. And if they have serious discussions about whether or not this is a good or a bad thing, record it, right? You jot down what they say. You make sure that they already feel, if you have doubts about the quality of this measurement system, very often even the committee cannot really agree. So they will feel that, darn it, even for them, even for our quality experts, it's difficult to decide which ones are good, which ones are bad. You put them on the spot, because your goal is not to have a perfect Kappa score. Your goal is to make good standards within your organization. So those people that make the standards, that set the standards, make the instructions, that often complain about the rest not being able to do a good quality control, they are your committee. Let them feel that it is difficult for them, even when they can discuss it, to set the standards. Now, of course, if they have an easy time, if they easily agree on these are good, these are bad products, that means that you have a strong system, so a strong golden rule to set the rest against, and you do have a good foundation for having this measurement system, right? So in either case, you are getting great answers. So either the committee cannot really get to the golden standard, then they immediately feel that there is a problem with what you called your quality standards, and they will, through their own discussion and sort of difficulty with, they have to come up with an answer, but they immediately feel that, oh, something is wrong. They will know that this is a problem, or they agree. And that means you have a very clear, at least, idea of what is good and what is bad. Now, this standard then goes into the same testing. You have operators A to E do the same check. They also jot down what's good, what's bad, and you make 5 of these plots. If you have the 5 people, each person gets their own plot, and then it will become committee versus that operator, right? So each of the 5 is committee versus that person. And they will all get their Kappa score. And then indeed you get this overview of how do most of our people do compared to the expert panel, who had, of course, all the advantages. And you can get these same conclusions, right? Is it 1 or 2 people who are not performing too well? That's probably the person is sort of, to blame is a nasty word, but the improvement efforts will go to the people. If it is 4 or even all 5 of them, the overall training system, the overall standards, what the committee has decided simply did not come across. Now, this will almost always happen if the committee themselves cannot even get to one answer. Then you are almost doomed to also have low Kappa scores of each of the individual people. But if the committee does have a very clear decision on this is good, this is bad, and most of the test candidates don't really have a good Kappa score, so they don't agree with the expert panel, then you need to seriously clarify what are the quality rules, probably work on instructions for everyone, work on a good training system for everyone. So you see that this analysis, if you set it up in that way, where you have your committee determine the golden standard, you do that in a nice meeting that you partake in, because as the test person, and it's not, you are probably not the person to partake in deciding which product is good or bad. If you happen to be a chief technologist or a quality specialist, get somebody else in to facilitate this, because you want a neutral facilitator there who is really looking at where are the committee members agreeing, disagreeing, what is difficult, what are the discussions. Jot it down. This is very good information for you to have to sharpen the quality rules and standards afterwards. You have the committee part, then you have a number of operators, quality control people. Also do it, you get a full scope of how your pass-fail measurement system is doing. Great system to use. And with these formulas, you can relatively easily even implement it in Excel if you don't have the specialist software to do it for you. Once you have this set up, it's not that big of a deal. In fact, I might just polish up my Excel file as well and share it with you as a nice freebie. Let me know in the comments if that would be interesting for you to have a Kappa calculator with this setup. But also, this is a great way for you to finally get to those pass-fail thingies, the pass-fail measurement systems that you cannot really use Gauge R&R on. So I hope that this was beneficial for you. Hit the like button if it was. If you have any other questions, besides if you would like me to work out such a file, also put that in the comments. For now, I wish you the best of luck using this to improve your quality control system. And as always, don't forget to also enjoy the continuous improvement journey.